In this video, I'd like to talk to you about a specific example that is mentioned in your text, but not worked out in detail. And the example is about a kid sledding on a sledding hill. So the story starts, I guess, a little bit before the first picture that's shown here. The story starts when the kid is being pulled up the hill by his friend. Before this, the kid in the sled is down at the bottom of the hill with his friend, and neither is moving. Then the friend in the red cap digs his heels in and walks as carefully as he can up the sledding hill, pulling his friend on the sled until he gets to the very top. And then at the very top, maybe the kid in the red hat gives his friend the tiniest little push, which causes him to slide down the hill, go over the hump, and slide down the hill to the bottom. We'd like to analyze the energy exchanges in the first part of this process, and then just cut to the chase and try to figure out how fast the sledder would be going at the bottom of the hill. So let's do the first part from A, where the kid and his friend are at the bottom of the hill, and B, where the sledder is at the top of the hill but not moving. I want to ask you to think about whether or not the process from A to B conserves mechanical energy. Now I want to remind you of something, that the total mechanical energy of a system is equal to the sum of its kinetic energy and its potential energy. And, to reiterate, mechanical energy is only conserved when any non-conservative forces are inactive. So when there's no so-called non-conservative work. Again, conservative forces are springs and gravity. And the reason why we call them conservative forces is because they have associated with them a potential energy. Non-conservative forces, basically everything else, like friction, air resistance, motors, and the metabolic processes even in your own body. So from A to B, I wonder if you think that the process conserves kinetic energy, conserves total mechanical energy. So I say it doesn't. I say that at the bottom, the kid has no potential energy and no kinetic energy. So at A, the total energy of the system is equal to 0. No kinetic and no potential. At B, however, although the kid is not moving here at B, we're going to say that V0 up here is equal to 0. He does have a fair amount of potential energy, and the way you calculate potential energy is with mgh. So there's no way these are equal. In fact, the energy of the kid on the sled is much greater than it was at the beginning. Where did that energy come from? Well, that energy came from the non-conservative work that the sledder did. So the work done by the kid in the red hat is equal to the change in energy, so just equal to mgh. And now if we want to evaluate this to a number, we're going to need to estimate the mass of the kid. How about we just say that he's 50 kilograms with his sled there? So what do you get if you calculate the final energy, the energy at, well, not the final, the energy at B here? It's the same. You're going to do 50 kilograms times G is 10 meters per second times H, 20 meters. So you need 50 times 10 times 20, and you get 10,000 joules. So the way you can interpret this is by saying that the kid in the red hat did 10,000 joules worth of work on the kid on the sled. In a sense, he loaded the kid up with a whole bunch of energy, 10,000 joules worth of energy. All right, now what happens as the kid goes from B to C, where he's at the top of the first hill, or to D when he's back down at the bottom of the hill. Now here, we can use the conservation of mechanical energy idea. And the reason why we can use conservation of mechanical energy is because after the kid in the red hat is done working his magic, there will be no work done by non-conservative forces. In fact, the only force doing anything to the kid on the sled at all is the force of gravity. You might ask that, let's see, the surface, the snow that the sled is resting on, that's a force, and that might be adding or taking some energy away from the kid on the sled. But the force that the snow exerts on the sled, if we assume that it's essentially frictionless, is always perpendicular to the direction the kid is moving. I mean, after all, if you were to draw a little diagram that showed the kid, let's say here, then the snow would push perpendicular to the direction that he's moving. And then gravity, of course, would pull straight down, which is partially aligned with the direction that he's moving. So we're getting a little in the weeds here. All I'm trying to say is that a surface can only do work if there's a friction component. Otherwise, the surface can only push perpendicular to the surface, which is perpendicular to the direction the kid is moving. Anyways, the long and short of all of this is that if we want to figure out how fast the kid is going at, let's say, D or at C, we don't have to worry about non-conservative work, so we can simply use the idea of conservation of energy. So if we want to use the idea of conservation of energy, then our approach is going to be different. We're not going to be talking about work and energy actually in joules. We're simply going to be making an equal sign. Here's how that goes. Let's say I wanted to figure out how fast the kid is going at C. Then I would do something like this. I would say that initially the kid has potential energy and no kinetic. So at B, the kid's energy is all potential energy. And at C, the kid's energy is some different amount of potential energy because the heights are different, but with some kinetic energy. And that since there's no non-conservative work, these in the end have to be equal. So I can set them equal to one another and try to solve the equation for the velocity at point C. Let's see how that would work. I would say, I'm just going to do some algebra here to see what results. How would I solve that for C? You might want to go ahead and plug in numbers, but I'll try to show you a different way. First of all, there's a mass in each one of those terms, so I can divide it out. And I can multiply both sides by 2 and bring this over to the other side. I end up with this. You might want to do this totally a different way. It amounts to the same thing. So if I want to find out how fast the kid is going at C, then I have to evaluate the formula 2 times g times the difference in the heights. We can do this more or less on the fly. 2 is 2, g is 10, so 2 times 10 is 20. And the difference in the heights between B and C is 5 meters, because I got 20 meters here and I got 15 meters there. So I have 2 times 10 is 20 times 5 is 100. So v squared is equal to 100, which means that the speed at C is the square root of that, 10 meters per second. Excellent. So when you use the idea of conservation of mechanical energy, you don't ever really stop and ask yourself how much energy in actual joules is exchanged. You just equate the initial energy and the final energy and solve for the thing that you want. Let's see if we can do the last step here without too much trouble. And the last step is to figure out how fast is the kid going when he gets back down to the bottom of the hill. So not too bad to do that. Maybe you can get a start while I clean the screen a little bit here. Start at B and ask yourself, what form of energy does the kid have at B? Well, same as before. The energy at B is equal to all potential energy. And what about down here at D? Well, he's back down to the 0 level where we're measuring all the heights from. So he doesn't have any potential energy anymore. So all the energy must be in the form of kinetic energy. So at D, all of the energy is kinetic. And since there's no non-conservative work, no friction, no air resistance, because we don't have a good way to take that into account anyways, then these have to be equal to one another. So it must be true that mgh equals 1/2 mv squared. This is going to be a bit easier to solve. The m's divide out because there's 1 in each of them. Multiply both sides by 2 and take the square root. So the velocity at the bottom in one swoop is equal to, and h here is how high he started up there, 20 meters. So let's just get an answer to this and then I'll just wrap this up. So 2 times 10 is 20, times 20 is 400. And then you got to take the square root of 400. That comes out to be 20 meters per second. Great. So I do want you to notice something about this. The conservation of mechanical energy approach is often faster because you don't have to stop and get actual energies in joules. And notice that we didn't need to know actually the mass of the kid at all, because if you do the whole thing algebraically, the mass doesn't matter. There's an implication here that's worthwhile noting, and that is, since mass doesn't matter in this energy analysis, then we can conclude that it doesn't matter whether the kid is heavy or not heavy, that all masses will get to the bottom of this ski hill, this sledding hill, at the same speed. The truth of the matter is, if you've ever gone sledding, that a heavier sledder will win every time compared to a lighter sledder. But the reason for that has to do with friction, which we've ignored here. So the friction force is approximately the same on a heavy sledder compared to a light sledder. And therefore, the friction force has a much greater effect on the lighter sledder, slowing him down more. So if you had to put money on a luge race and one of the luge contestants was heavy and kind of fat and the other one was thin and kind of skinny, I'd put my money on the heavy one every time. But in our analysis, that's not revealed because it all starts from the fact that we're ignoring friction, that the non-conservative work is 0. So I hope that's helped, and then you'll have to try to put this into practice with some end of chapter problems.